Hello everyone, Norman here with McWane Science Center, and welcome to SciSparks. Our universe can seem pretty chaotic, with things flying around and colliding all the time, whether that be particles, rocks in space, or marbles here on Earth. But it turns out that chaos follows some predictable rules that come from something as elegant as symmetry. You may have heard of Newton's laws of motion. You know, the ones that say an object in motion will stay in motion until acted on by an outside force, or how for every action there's an equal and opposite reaction. Well, there are some other laws of motion that our world obeys, including one called the conservation of momentum. See, momentum is this fancy term for the amount of motion an object has. Or you could say it's how forceful the motion of an object is. Either way, it depends on two things: mass of the object and the velocity of its motion. When two things collide, momentum determines the impact of that collision. A ball bearing hitting a ball bearing of the same size knocks it away. But if that same ball bearing hits a bigger one, it bounces off instead. But what do we mean by the law of conservation of momentum? Well, no matter what's going on in any system of objects, the total amount of momentum is always the same. The more momentum an object has going into a collision, the more momentum an object has when it comes out of that collision. We can see this easily with a toy car. When the car rolls down the ramp and hits the ball bearing, it pushes it forward some amount. If we increase the height of the ramp to build up more speed, the strength of that push is increased. If we decrease the height to have less speed, the strength of that push is decreased. Similarly, if we make the mass of our ball bearing smaller, which makes our car bigger, then the strength of our push is increased. Whereas if we make the mass of our ball bearing bigger, which makes our mass smaller, then the strength of our push is decreased. We'll spare you the math, but that increase and decrease balance each other out, so the momentum put in equals the momentum that comes out. Now, some collisions might look like they don't conserve momentum, but really, they just don't conserve kinetic energy. See, collisions can be elastic or inelastic. The objects can appear to transfer their motion perfectly, like billiards on a pool table, making the collision elastic. Or one object can seem to absorb the motion of the other, like catching a baseball in a glove, making the collision inelastic. In either case, momentum is still conserved. It's just that in the inelastic collision, that momentum is carried over into moving particles as heat and sound, or into forming the glove. But why is momentum conserved? Well, Emmy Noether made the brilliant discovery that it all comes down to symmetry. Specifically, the fact that no matter where you are in the universe, the laws of physics don't change. If I roll this ball here, it obeys the exact same laws of motion as if I roll it here. That means that motion can't just vanish from one spot to the next. At any given point, every single particle in a system has to keep its motion going. And the way that motion is transferred can't change from place to place. To achieve this, overall momentum has to stay constant. Now, for my favorite way to see this conservation in action, let's take a look at this device called a Newton's cradle. It's a simple setup: 5 metal spheres hanging next to each other as closely as they can fit, and when I lift one of them on one end, and it'll keep going until all that momentum is transferred into the air around it as heat. But remember, if momentum is conserved, then if I lift 2 of the spheres, we should get more motion. All right, what was once in motion needs to come to rest now. Thank you for watching this episode of SciSparks. If you enjoyed today's episode, let us know by leaving a like. And to catch new episodes as soon as they're released, don't forget to subscribe. Until next time.